Okay. What we're going to be looking at now, we're going to start talking a little bit more about some of the ceiling floor load, some of the other portion of the heat load. But again, just to go back to the spreadsheet that I have out there, and I really encourage you guys to use this as a part of your project if you're at all able to. Now, when you open it on the iPad, the little drop downs for the state and then the city are difficult to find. They're actually up on the address bar. So when you click on the design, city, and state, the little drop down is very difficult to find, but it is there. So you'll have to select Pennsylvania and then York, okay? Now there's two numbers on here that are relatively important that it comes up with that you're going to need. You have over here, and I just took that too big. Okay, over here you have an HTD and a CTD. Once you select your city and state, this is your heating temperature difference and your cooling temperature difference. Basically what that is, that's the difference between the indoor design heating and the outdoor temperatures, okay, the outdoor design temperature. Same thing with cooling. This is our inside design temperature, and then you have over here the outdoor summer temperatures. Okay, so again, we have the heating temperature difference and the cooling temperature difference. This is your delta T. Okay, so that's becoming very important. Because when you come over to, we talked about glass, we talked about windows. Okay, so when you come over to the glass tab, which should be the next tab that you work with, okay, you need to come over to the tables I gave you. Specifically table number 2. Okay, it's the one, it was one of the handouts. It's earlier in the course. I uploaded a bunch of tables for you. You need to find the window that's in your specific room, and my guess is they're duplicated throughout the house. You need to find the appropriate window, like in this case. Is it double pane glass windows with a storm, or is it just double pane windows? Okay, in my case, and I'm going to try to do this a little bit honestly with what I have here, okay, we have metal frame windows that are double pane. Okay, and again, the winter temperature difference, and I'm going to do this initially for York. I'll probably change this as we finish up. But my winter temperature difference, if you remember, for your area is 58 degrees. So I'm always going to go higher. I'm never going to round down on temperature differences. So if it's 58 degrees, I'm always going to go to the 60. Okay, so even if it's 56 degrees, go to the 60. I'd rather be a little bit oversized, not a ton oversized, but a little case. I have low emittance glass with a metal frame. Okay, so we're in this column, and I have metal frame windows, and I have again, it's the low emittance glass because we have a film on it. And so my multiplier, okay, my heating multiplier is 28.5. So I'm going to come over to the spreadsheet, to the glass tab. Okay, and I'm just going to put on there, it's number 3, it's double pane, low emittance, and I'm just going to say low E, okay, metal frame. And my heating value is, again, that number from over here on the chart, the 28.5. So that's basically going to go right there. And my cooling value, okay, we're going to pull from the table number 3. Now, cooling values are weird. So again, I got to come down and I got to find what it basically, you have to find the different, like the heat absorbing glass, reflective coating glass, okay, and you have to find like so no external shade. Mine is not clear glass. We do have a reflective coating on it, okay, and it's double pane. So we're looking here, okay. Do I have internal shading? Yeah, I have. We might actually, I'll say Venetian blinds because that's more what we have. Draperies or Venetian blinds. Okay, so, and my temperature difference is this across the top here. Now remember, that's cooling temperature difference. So we want to come back over to my J1 form. My cooling temperature difference is 16. That's again for your area. My area would be completely different. So 16, I have a choice of 15 or 20. Again, I'm always going to go with the higher number on the temperature differences. So I'm going to come down here, and it's in this column. So I actually need these numbers because I have to have the north, which is 12. I have to have the, oh, what did they say? I don't think they're asking me for a northeast. Yeah, they are. So I need all those numbers in that column. Okay, so I need the 12. I need the 24. I need the east, which is the 34. I need the southeast, which is 30, and the south, which is 19. So I need those, all those 5 numbers, okay, and they're just going to plug in right here. So I'm going to do the 12, I'm going to do the 24, I'm going to do the 34, I'm going to do the 30, and I'm going to do the 19. So for every different type of window you have, this is what you need to do, okay? So if your house like has 16, 17 different types of glass, you get to list them all out. Okay, if you have skylights, put them down here. Now most houses, even if you've done a remodel, you won't have over 2 or 3 different types of windows, okay? Windows seem to be pretty standard through a house. Again, if you have a remodel that's been done, or if you had done an addition, it's going to have additional types of windows. Okay, so that's what we need to do on this sheet with the glass. Any questions on the glass?
If all our windows are the exact same, just different sizes.
One line.
Okay.
And hold that thought, because as soon as I do doors, I'll show you why it just doesn't matter.
Okay.
Okay. Over on doors, we're going to do the same thing. Now, we're not talking interior doors. I'm talking exterior doors. So again, we need to come down to our tables, okay, and we need to find doors, okay. That's sliding glass, French, wood doors, okay, or metal doors. Again, table number 2 gives us our heating, okay. So you're going to come down on table number 2, and again, I'm going to go with this one because my front door is a fiberglass door. We'll go with the 60. Again, that's the York area, and I have a storm door. Okay, so it's a polystyrene core with a storm door. So my heating is 19. Okay, so again, I'm going to come in here. I'm going to say number 11 metal with a core and storm. Okay, I'm just going to type that in that first line. 11, comma, metal, poly, core with storm. Okay, and I'm actually going to jump over to table 4A here. Okay, because I want the U value. I don't need this value, but okay, so I'm going to jump over to 4. Okay, because it's saying come over to 4. So we're going to come over and say, again, the poly core and storm is right here. And temperature difference. Here's that U value I need over on the right side, 0.317. Because again, we're going table 4 here. So 0.317, that's my U value. That's how you do doors. Okay, find the construction. You can enter up to 6 different door types. I do have some back doors as well that are more the French doors, okay, because they have a lot of glass through them. Okay, so again, table 3 if there's window and glass doors, okay. So I do have some French doors, and they're all facing north. So this again is glass, tinted, reflective coat. Okay, north facing, they have Venetian blinds inside the glass. So, and again, well, it's not Venetian blinds, it's more roller shades. Inside the glass, temperature difference we said was 20, so I'm going to go with that column. And I'm just going to jot that down because it's much easier. And so again, glass doors, you treat them as windows, basically. Okay, again, glass doors. Okay, treat it as windows. Ignore glass if the glass area is larger than 51% of, or less than 51. Classify as a French door under the glass tab if the glass area exceeds 50% of the door area. So be careful about your glass area. So here, I'm going to say, again, we're going to say 3 French door. Okay, and I'm going to fill in my 13, 15, 16, 16, 14. Okay, and then I'm going to go over to my other chart. Okay, and I'm going to find there is one here for French doors someplace. There we go. And the French doors, obviously, we have wood frame. 0.342. And then I'm just going to, I always save as I go just because I hate losing stuff. Now, back over to the J1 form, okay? This is that first form that you put your state and information in. Okay, so for any room here, okay, you're basically going to say windows and doors, what do you have? Okay, so, okay, so you're going to come in here. Let me slide over here because I need to make sure you guys can see it. Okay, you have the glass schedule. Okay, so what you're going to do is you're going to select from here, okay, and it's going to all go on that, it's going to go here. Okay, so you have a glass schedule. So you're going to select, okay, I have a French door. Okay, glass faces north. Okay, and you're going to give it like the height of opening. In my case, the doors are 7 feet. I have, let's see, that's a porch, so I have a 10-foot overhang. Okay, top of opening to overhang, it's like 2 feet below the overhang. Is there any adjustment for protected window or French door? Yes. Is there any cooling adjustment? Nope, I don't have any screens on it or anything else like that. So you're going to come down your glass schedule And this is where you're going to end up listing most of your windows. Okay, questions on that? Okay, so what we need to do for basically, this is assignment 3 if you're doing it on a spreadsheet. You're actually coming through and just doing it here. You can also hand in, if you want, just the actual, you can hand in the actual just manual calculations for just, I need to know that you've done it. So if you want to put it in a spreadsheet, that's how you're putting it in the spreadsheet. Okay. Questions? Then, when you come down ready to put in the net area, let's say this is a, I'm going to say living room. Okay, so if the room has a living room, and if you have a 7x3 door that's 21 square feet, okay, you type in the square footage. This is where I said it doesn't matter on the initial screen to list every window separately, because you're going to do that here based on the room. If the window isn't in the room, you're not going to put anything in here. Do you follow what I mean by this? Anybody? I forget.
Yeah.
Okay, I forget who, was it you who asked me earlier on the number of windows?
I had the same question, but it was Chris that got it first.
Okay. So again, you're going to, based on what you put here, you're going to go to your glass schedule, and you'll do the same thing. There's a door schedule someplace, but you'll do the same thing. You'll just list out, this is where you're going to put your different directions. So if I have a French door facing north and a French door facing northeast, it would go, you'd have 2 lines. If I have windows facing south, you just need 1 line for all your south-facing windows. And again, height makes a difference. If you have windows facing all 4 directions of your house, but the windows are, okay, they're the same windows, the same type of glass, you're going to have 4 lines for that window because direction makes a difference. Doesn't make much of a difference in heating load, but makes a big difference in cooling loads. Now, do most houses have an overhang on at least 2 sides of the house? Do you have an overhang over your windows on at least 2 sides of your house in most construction?
Yes.
Yeah, the eaves. The roof eaves. It's going to be either 2-foot or 3-foot overhang, and just estimate how the distance from the top of the window to the overhang. Okay, that's that third white column here. And let me blow this up because I know this is tough to see a little bit. This third white column here. Okay, so I have, in my house, I have a double pane window I have 1 window on the west side of the house. Oops. I have 1 window on the west side of the house. The height of the opening, it's a little narrow window, so it's only 2 foot high. Overhang distance, that side does not have an overhang. And the opening to the top of the overhang is 0 because there is none. Okay, do we have an adjustment for a window? Nope, no adjustments, and no overhang adjustments because well, actually, yeah, there is a screen in there. Okay, so, and then on my east side of my house, I don't have any windows. Front side of the house, which is south facing, it's all double pane. Okay, facing south. Height of openings, they're actually pretty large windows, so they're all 3.5. They were custom. Distance from the overhang hangs out on the front of my house by 3 feet. We have a large roof line. And top of opening to overhang is, we'll say, 2 feet. No adjustments other than screens. So basically, 3 lines take care of all of the windows in my house on the glass schedule. 1 line takes care of all of the doors on my house on the door side, and it's very simple because it's a front door, and the rest of my doors are classified as French doors because of the amount of glass. Any questions on that? And you'll see this will start to populate, so you'll go through here and you'll just, if it isn't in the room, okay, so for example, the living room does not have any east or west windows in it, I just won't enter a number here. No number entered means it doesn't exist, and it's not going to create a cooling or heating load. Does this make sense?
It's Chinese.
Where did I lose you?
No, I'm kidding. It's fine.
Okay. Yeah, well, I mean, in all seriousness, I do want to make sure you guys get this because this is sort of important.
I am a little confused to the different rooms, how you have living room there, but you just said you didn't add values. Why did you type
Yeah. Okay. Over here, you see where I have this area here that I've just shaded?
the whole thing?
No, over here where the east, west, south. Do you see this area here?
Okay, yeah, your thing's jumping up a little bit. Yeah, I got it.
Okay. This is automatically put in here from what you do on the glass and the door schedule.
Oh, okay. I see.
Okay. So on this form, if I don't have this in the room, I just won't enter an area number.
Okay.
Okay, because it isn't there. So as you go across on your rooms, like if I scroll over here and if I have a, let's say, now dining room. Okay, I have windows. These are 3 by 4. That's 12 times 2. So that's 24. So I have windows, and it's actually north facing, so I have to add one. But I won't have a French door there.
Right.
Okay. So I'm just okay. So only use the values that are there. Now, when you get down to doors, okay, remember, you added doors here. You have a door schedule you put in there. But when you get down to the doors, which is yellow, by the way, anything in yellow is going to have a drop-down list. So I have a metal front door with a storm. Okay, it's actually in the living room. Okay, it's 30, so it's 3 feet by 7 feet. So again, 21. I'm just going to add that there. Okay, so again, as you go down here for each room, you are only adding what's in the room. Make sense? Is anybody lost on this? Okay. So that is so far what we've talked about and how to add it to the spreadsheet. And again, I haven't done my own house here in Florida, as much as I hate to admit it, but I'm going to do my own house so that I can show you how it goes as we go. So I'll always have a sample. Again, the reason I'm encouraging the use of this spreadsheet is because I want you guys to keep a copy of it. If you ever have to do this in the future, either for a job site, friends, family, whatever, or to figure out what's wrong in your own house or what's right in your own house, I want you to have a copy of this sheet and understand it, because this sheet is probably one of the best ones I've seen. Okay, and I know it's a little bit of a pain on the iPad, but you also have access to Office 365 online. You can open these up in a web browser using Office 365. There's other ways to access it, but I want you to have it. On your assignments, would I ever grade you down for doing this on paper? No, I'm not going to. Okay, but this just, it makes it easier. If you submit these spreadsheets to me, please save the sheet with a name, including your name in it. Okay, so don't just turn in a whole bunch of the same name sheets. So put your initials in it or something, because when I open these up, I need to be able to keep them separate and know who I'm opening up. Okay, I do need to talk about our PowerPoints a little bit today, because we do need to continue that on. Are there any questions on the sheet before I move forward?
If we use this sheet to do this part of the project, how do we send it to you?
You can upload it in the assignment, or you can email it to me. I don't care.
Okay.
Okay, you can upload a file to the assignments. I have them all. Yeah. Okay. Either way, doesn't matter. And just it's a point in time, because it's going to continue to evolve.
All right. So never mind. Okay, that's fine.
Question on that?
No, I'm good.
Okay. Because I'm sure somebody else had the same question, so. Okay. Now, we finished off taking a look at the different types of windows. I looked at different types of door construction. We talked about some solid core wood door issues. We talked about some cracks in foundations, and we talked about outside observations. Okay, what we really haven't gotten into in our presentations yet is the fundamentals of how to do the heat load and what we're actually looking for and why we do it. Okay, heat load calculations are a major pain for most contractors. They hate doing these things. I don't understand exactly why, because I think it actually makes a lot of sense, but sometimes I'm a little strange like that. So it comes down to the same equivalent. Would a cabinet maker cut boards without measuring first? Okay, probably not. So why would we install an AC system or a heating system without knowing what's in the house? Okay, the way it used to, I mean, real estate agents, some contractors, some salespeople still don't have a clue what a heat load is. Okay, and that's the point this is basically trying to say. Your customer will not necessarily have a clue what a heat load is. They'll have no idea what you're talking about. When you start talking, oh yeah, you want to add a what? And we need to do a heat load to make sure your construction is going to handle it. They're not going to have a clue what you're talking about. Okay? It used to be that you'd call a contractor and say, I need a new furnace. The guy on the phone would say, how many square feet is your house? And they'd use a rule of thumb measurement to size a furnace without even walking out to the house. A matter of fact, I was sitting here watching TV last night, and I don't know if you guys are seeing the same type of ads we are, but we have all these contractors who are trying to sell new equipment over the phone right now because they're not allowed to go out and visit people's houses. So they're giving quotes for equipment replacements over the phone. And it just doesn't make any sense to me whatsoever how you can do that. So they'd say, how many square feet is your house? They used to say, okay, it's close enough was good enough. These old rule of thumbs are going to get you in a lot of trouble with building officials. It used to be they'd say 1 square foot or however many square feet is 1 ton of cooling. I've heard different contractors use like 400 square feet as 1 ton of cooling. I've heard another contractor use 1,200 square feet as 1 ton of cooling. Okay, so, and they used to use any number in between. I called it the stand at the curb and gets method. Okay, they'd also say 1 square foot requires 30 BTU per hour of heating. Again, that was a standard that they used for many, many years. When I first graduated from Porter and Chester and started working in the field, okay, I worked for a guy who was actually a very good contractor. He was excellent. Good guy to work for, but he used to use the 400 square foot as the rough number, and then he'd come back to the office and do a full load count. But the old close enough is good enough is not going to get you in trouble. We also had people who, and this was a lot of times with the contractors, new construction, okay, they'd say, I'd rather be well oversized than get called back on the coldest day of the year, and I haven't been sued yet. Okay, this was the avoid lawsuits by shifting the burden to the customer. Okay, in other words, the customer paid more monthly heating costs because the guy didn't want to be sued and didn't want to do a proper load calc. Okay, again, we still have contractors out here in the world that do this, but who pays the price for it? It's going to be the customer. Okay, the customer is going to pay for the higher heating bills in the winter months. Okay, he'd rather have legal protection rather than do it right. Then, we talked about this a little bit yesterday. Guy says, I did a house like this a couple years ago. It can't be that much different. Okay, yup, house might have been on the side of a lake, might have been on top of a mountain. But yup, because it was the same house, they're going to do it the same way. Well, that doesn't work. Also doesn't work. Okay, this contractor's more into the size. If it fits into the space allowed, it's properly sized. In other words, if the furnace fits, it's properly sized. Okay, contractors who are doing entire subdivisions may buy a truckload of a single-sized piece of equipment but not realize the way the house faces, if it's on a hill or not, is going to be a big difference for air conditioning and heating costs. So again, this is all excuses that we've all heard on why people did not do load sizing. The consequences of improperly sized equipment, it's grossly oversized. That costs more to install and more to operate at a reduced efficiency. And I'll explain that in a minute. But if the estimated heat loss is too low, the building will be uncomfortable during the cold weather. It will be the opposite way if the air conditioning is sized too big. Oversized air conditioning does not properly dehumidify. Okay, it feels like you can have this, I call it the cold clammy effect. Okay, you'll walk into the house and it will feel moist, almost like a walk-in refrigerator. Feels moist, feels cold and clammy. It just is not a comfortable environment. Grossly overestimating building loads, okay, for example, if the furnace is too hot, too big for the space, okay, it's going to overheat and it's going to cycle on and off on its high limit control, and every time you relight a furnace, you have a loss of efficiency. So those of you who've had gas and oil, you may have talked about that a little bit during those courses. Those of you who still have to have the gas and oil courses, you'll talk about those. Okay, but every time you restart a furnace when you're cycling on and off on high limit, you have a loss of efficiency. Be careful. If you don't know for sure, you're guessing. Okay, again, I keep coming back to the contractor who stood at the curb and holds two fingers up like they're measuring a fish and say, okay, if it's between these two fingers, it's a 2-ton system. You don't know that. Okay, earlier this term, I showed you a picture of a little tiny house, 500 square foot house. It was one of our discussion board posts, I believe, on air quality. Okay, 500 square foot house, that system had a 2.5-ton system in it. My house has a 2.5-ton system in it. Okay, big difference between house size. That system was grossly oversized and there's no way it would ever dehumidify. So again, if you don't know, you're guessing. So what do? We do heat load calculations. This is what we're going through for your final project, and this is the whole point of this course. This is why we've done everything we've done so far, because it has to be tailored to the need of the house. One size does not fit all. Okay, we want to maximize comfort while we're minimizing cost. In other words, customers need to be comfortable and not pay a lot for being comfortable. And the system needs to work behind the scenes without being obvious it's there. Again, HVAC, we want to be silent. Okay, we want the system to just operate it. We want it to just work, and the only interaction the customer should have is the thermostat. So, does a properly sized and installed high-efficiency HVAC system assure achieving the comfort and cost goal? For example, okay, let's say if you put a 90 miles per gallon carburetor in a car, will it be a fuel-efficient car? Not necessarily, okay? Just because it's properly sized and installed high-efficiency system does not mean it's necessarily going to meet the comfort and cost goal. Okay, a building like a car is a system. The heat loss evaluation is looking at the system. In other words, if it fits, is not a good measurement of will it work. Okay, we have a system we have to look at. Okay, it's very important to look at the entire building as a system. I've seen way too many people who just walk into the basement, crawl up into the attic, and just look at the box sitting there. Okay, these, I call them the callback kings. They're the ones who keep getting called back over and over and over again to a customer until sooner or later the customer either gets fed up with the company and finds another contractor, or gets fed up with the technician and demands a supervisor come out. And that supervisor is going to walk out, and because he's usually more experienced and understands the building as a whole, he's going to walk out and notice the customer added a new porch, a new sun porch, and threw some duct work in because everyone likes doing it themselves from Home Depot, and realized, oops, the system isn't sized properly anymore. So again, this is the point of this. You need to be able to realize the building components are a big part of computing heat loss. Okay, so how important are all building components? In some cases, they're less important than they think they are. For example, do I care about a statue in the front of a building with heat loss? No, I really don't. It makes no difference whatsoever. Okay, so different components have different needs with heat loss. So, again, as I said yesterday, okay, the first thing I do when I walk up to a house that I know I'm going to have to do a heat load in, or I'm there to look at a problem, okay, is I walk around the outside of the house, okay? Now, I'm looking for the location of windows. I want to see if they have a reflective glazing or covering on them, okay? I may do some drawings. Some cases, again, this comes with experience, I may take outside dimensions. I might take just a length and a width of the house if it's sort of rectangular. And the reason I do that is once I have my inside dimensions, okay, I can tell what the outside wall dimensions are. I can tell how thick those walls are by comparing my inside dimension to my length and width measurement of the house. Okay? When you're looking at the outside of a house, as I showed you yesterday, I went through like 4 slides yesterday on the outside of the house to like, we looked at the windows, we looked at like what is it you see here that could affect heat load. What you can see from the outside is what the weather can see. Okay? Then you take some inside dimensions. We want to, while we're looking at this, we want to look at the quality of the construction. Now, do I maybe necessarily make comments to the customer about the quality of the construction? No, because who knows, their uncle may have been the builder. Okay? I had a technician who worked for me at one time when I was running a service department, who went out to a house and because it was the first time we serviced that house and we didn't know the history, the technician went out to the house and actually really bashed the construction of the house and said, this is the cause of your whole problem. And what they didn't realize is that the woman's husband was a builder, and he's the one who built the house. Yeah, it was a crappy house, crappy construction, but you got to be careful what you say to the customers. Okay, you can cause a family war. Obviously, obvious envelope issues. Anytime we're talking about a building envelope, we're talking about anything separating the conditioned space from the unconditioned space. Okay, obvious breaks in the building envelope. Remember, we talked about the cracks in bricks. Okay, that can be a real heat load issue. Okay, you have to be sensitive on how you deal with it with the customer, okay, because the customer may not realize or may be planning on getting it fixed, or even more sensitive sometimes is the customer might not be able to afford to get it fixed. You don't want to rub their face in it. You want to take a look at how much wall is, including the basement, is exposed to weather. Remember the picture I showed you of the windows, the basement windows that were elevated off the ground and had under the porch. Okay, how much wall, including the basement, is actually exposed? Makes a big difference. Okay, that we look at the area of the walls. Okay, so again, your next step, one of the next steps in our project is going to be looking at the areas of the walls. One of the things I'm trying to get you to do is get your net wall area. Okay, there's a reason for that. Okay, because we have to look at the area of the walls. Anytime we have area that's doubled, the rate of heat transfer doubles. That's not thickness, that's area. Okay, square feet. If a wall is 8 foot tall and 10 foot long and it's changed to 20 foot long, the rate of heat transfer will double. Again, we have to remember our formula. The Q, and that's a Q, sorry, equals U times area times delta T. Okay, so anytime we increase the area, we increase the heat transfer. Okay, delta T is a shorthand difference between two temperatures. You're going to see this all the way through your trade. Delta T is just shorthand difference between two temperatures. Temperature 1 minus temperature 2 equals delta T. It is very possible sometimes to have a negative delta T depending on where you take your temperatures. But when you put it into a formula, unless it specifically says to use that negative, just drop the sign, use the absolute value. Okay? So again, you can end up with negative delta T's. It happens in air conditioning all the time. But drop the sign and just use the absolute value. Okay. If the outside temperatures changed the original delta T, then the rate of heat transfer doubles. Okay. In other words, if our original delta T is 6 degrees and our new delta T is 12 degrees, the rate of heat transfer doubles. So the colder it gets, you're going to lose more heat. The warmer it gets, you're going to gain more heat. Doesn't matter if the area changes, okay, but you're going to gain more heat or lose more heat based on the same area. Again, remember our formula. Q equals U times area times delta T. Okay, this is an example of this. Okay, our set point, which is our thermostat set point, indoor temperature 70 degrees, outside temperature 60 degrees. Delta T is 10 degrees. If the outside temperature changes to 50 degrees, my delta T now doubles. It's 20 degrees, and the rate of heat transfer will double. Okay, this is why insulation is so important. So, where we're at in this whole thing, you're going to calculate the specific heat loss for each room in a building. Okay? We want to make sure we do things on a room-by-room basis. That comes back to our spreadsheet that we had. Okay? You're going to do room-by-room basis. Okay? So the first thing I would do is, after you put your windows and stuff in, come across the top of the spreadsheet, and in the white labels over the room columns, put a room name in, or room designation, and this should match your drawing somewhat, so you always know where you're looking at. Okay? And then you can put in your window and door areas. Okay? We'll talk about walls in a few minutes. Okay, but you're going to come in and put in your window and door areas. So again, room by room. Then, once we're done with this all, we're going to add all the rooms together to determine the total heat loss and heat gain for the entire building. Why do I care about entire building heat loss and heat gain? Why do I need that number? Anybody? Why do I care about heat loss, heat gain for the entire building?
To size your heating system, I would imagine.
Yeah, I can't size the main system, the furnace, the air handler, the boiler on a room by room basis. I need a total. Okay, and then we're going to add some stuff to it. We're going to add losses for air exchanges. Okay? We're going to add losses, I haven't talked about it yet, for ductwork. Ductwork in unconditioned spaces has heat gain and heat losses. Okay, we're going to add a little bit for what we call infiltration. That's the uncontrolled air exchange. Okay. So the heat load calculation influences the system cost, the efficiency, and quite honestly, most important, the customer satisfaction. A properly designed system, you will get 0 complaint calls on. Okay, if the system is not properly designed, there's going to be hot and cold spaces. Now, the best systems have a higher cost. Okay, so you may work for a contractor that actually gives the customer 3 options. I call it the good, better, and best method, which is a great way to do systems. Okay, good, better, and best. Okay, the best is what we present up front first. Then the customer says, well, that's going to be a little bit too expensive. So we remove some of the efficiencies, some of the things we can remove without cutting quality too badly, and we give that as the better option. Okay? And then the customer says, well, I'm sorry, I have 14 bids that are lower than yours. At that point, you as a contractor have to make a decision. Do I want to give my lowest quote option, which is not going to make the customer comfort? Okay, it's not going to keep the customer happy other than price, or do I want to walk away from the job and say, you know what, we're not in the same market. I'm sorry, I can't install that low cost of a system and guarantee you comfort. Okay, so I usually walk away from it if it gets below the best, okay? I just don't deal with price shopping. I don't do that too well. So, but a lot of contractors do give the 3 options, and if the customer wants the cheapest possible system, they'll install the good, and they'll end up with service calls, and I don't deal with that. So, again, system cost, efficiency, customer satisfaction. The design heat load of a building is an estimate, and this is a very important thing. You've heard me say a number of times through this term that everyone's answers are going to be a little bit different. Okay, it's an estimate for the rate at which building loses heat during the near minimum temperatures. Okay, so again, when we select the York climate, and it's different from the Orlando, Florida climate, okay, we're selecting the minimum temperatures in the winter months and the peak temperatures during the summer months. Now, do you always hit that minimum temperature? No, but it's over a period of time they're looking at the minimum temperatures. But the key word is this is an estimate. That's why I don't care if you're off by a couple inches or even a foot. Okay, it's not going to make a difference in the grand scheme of things. Do I want you to be off 10 or 20 feet on a building length? No. But if you're off a couple inches for wall space or something like that, interior wall space, it really doesn't matter because it is an estimate. Okay? What we don't know when we're looking at a house is we don't know the quality of the installation of insulation materials. There could be big gaps in the insulation. Okay? We don't know the overall construction quality. I don't know what's in the walls. Okay, I don't necessarily know what's in the basement cinder blocks. I don't know if they were insulated. I don't know if they were concrete filled unless I can see the top of them, and then I don't even know if it was done all the way through. I do not know the construction quality, especially in some older houses. I'm not even sure the people who constructed them are around anymore. So we also have insulation materials. R values are not consistent. What did I say happens to insulation as it gets crushed? What happens to the R value? As I crush insulation, as I compact it, what happens to the R values?
Goes up.
R value drops. U value goes up. Yeah, R value drops. It's going to be less insulation. It's going to be, the heat will flow through it more easily. Okay, this comes under building materials shrinking and shifting. Remember the bricks the other day of the shifting house? Okay, the house has shifted. All of a sudden I have a heat load problem. Gaps, paths for leakage, unintentional thermal bridges. Okay, we haven't talked about occupant influence, like going in and out, opening windows, changing set points on thermostat, leaving vent fans on. Cooking and baking, an oven puts off a lot of heat. A dryer removes a lot of air. Okay, a dryer is one of the biggest uses of, basically pulls heat right out of a building. Okay, 600 cubic feet of air a minute can be pulled through a dryer. Okay, and that's a lot of air. Well, the cold air has to come in someplace. We also have effective wind on building infiltration. Okay, if the wind is blowing on the side of the house with the crack in the brick, it's going to blow cold air into the wall spaces, and in turn the wall will feel cold and put off and absorb the heat in the building. Okay, gaps, paths for leakage. Occupant influence we talked about. Okay, people moving thermostats around, people leaving doors open, people leaving windows open. Okay, couldn't even be people, might be pets. Dog doors get stuck open. Okay, FIO comes in and goes out all the time. That's heat loss or heat gain depending on the time of year. So, when we talk about temperature difference, which is delta T, area, and U value, these are all considered transmission losses. Okay, these are through the walls. Okay, it's considered transmission losses. Air exchanges. This would be like things blowing through cracks and crevices, doors being left open, or purposeful air exchanges. They're called infiltration losses. Okay, again, there's a big difference. Transmission losses and infiltration losses. Transmission losses, once I've installed like the best windows ever, insulated walls and stuff like that, I can't do much about. They're relatively constant. Infiltration losses vary over time. Okay? Without a temperature difference, there's no heat transfer. So if my indoor and outdoor temperatures are both at 70 degrees, we're in a state of no heat transfer because hot will always move to cold. All heating systems consist of devices that convert one form of energy to another. That's what we're doing. We're converting either fossil fuels, gas, or oil to heat. We're converting electric to heat. That's all we're doing with a heating system. Convert one form of energy to another. Okay? The type of material through which heat flows or moves affects the heat rate of transfer. We've been talking about that. Different materials. Okay? Which is why we have all these tables. Okay? The design air temperature makes a big difference. Okay? The air temperature at which the HVAC system is designed to maintain inside design temperatures or to operate against outside temperatures. Okay, dry bulb temperature, 97.5% of the time. Okay, that just happens to be one of them. Okay, sources of data, ASHRAE. is our primary source of data. They take, different software companies take that ASHRAE data and build it into their software. Okay, but ASHRAE is the primary source of data. Okay, and it's available on the web. If you look up ASHRAE temperature heating design temperatures, you'll find their tables. You can actually pull a web page that you can plug in your location and you can get all the information. Okay, now, we have to mention it, believe or not believe, that's up to you, but design temperatures are changing because of climate change. Okay, and in some areas, it's pretty significant what's going on. Where you used to have a snowpack around a building, and believe it or not, snow is an insulator, okay, you might not have any snow anymore, but still might be getting these extremes of cold temperature. Makes a difference. Okay, extreme temperatures make a difference. My first year in Florida, we had 3 frosts. I know, tell me to shut up, but we had 3 frosts. Okay, for the last 4 years, we haven't had a frost once. Okay, there's a significant change. Things are getting drier. Okay, we see it more in the south than it's seen in the northern part of the country. But there's changes in temperatures going on. Okay, when we compare 1977 to 1997 data, okay, increased dry bulb temperature about 2.74 degrees. Not a lot in the grand scheme of things, but it could be a quarter of your outdoor to indoor design temperatures, which increases system size. Okay. A different version of dry bulb increased 1.42 degrees. So again, depending on what you're looking at. Annual dew point temperature increased by 0.99 degrees. Not a big difference, but it's a difference when it comes to latent heat for cooling. Heating degree days. Now this one is the really interesting. Okay, heating degree days decreased by 427 degree days. Okay, now a heating degree day is anything under 65 degrees. Okay, the average temperature for a day under 65 degrees gets all added together, and it's decreased over time. Cooling degree days increased by 245 degrees. Okay, so again, cooling degree days have gone up, heating degree days have gone down. Okay. So the set point, when we talk about set point, this term has come up a few times. It's the desired temperature. Okay, it's what we want to be able to maintain the inside temperature at. And some areas mandate what our minimum indoor set point is by law. Okay, and it's actually, the system has to be able to maintain this. Sometimes it's by law. Normally, it's 70 degrees on the heating side and 75 degrees on the cooling side. Okay, that's what our normal mandated set points are. Now, your customer may want to maintain the house at 65 degrees on the heating side and 70 degrees on the cooling side. That's fine. Okay, but the heating system needs to be able to maintain what the required set points are. Now, if your customer says, I like my house colder, I'm going to come over here to this first page on this chart, and I'm going to change the cooling design to 70. So I would come up here, okay, and I change my temperature splits. If he wants to if I know that primarily they're going to maintain, as long as I'm within the range, I'm fine. Okay, because 70 is under 75, so the system has to work more. 65 is under the 70. Okay, system probably has to work a little less, but it's still, I know I can maintain it. Okay, so for legal purposes, I'd probably do that because I'd explain to the customer, it's under, your 65 will be under the 70, the system will work less. Okay, because I have to maintain what's mandated by law at least. Okay. The body set point is 98.6. Okay. You can either get some cooling or you can get some heating to maintain that temperature. Okay, system design delta T. And I've said this a few times, but we keep repeating it, but it's important. The design temp minus the design set point, okay, is my system design delta T. So this is my outside. This is my in. This is my system design delta T. And again, if you're using this spreadsheet, it will automatically, you'll have that right at the top of the sheet. Okay, now we've talked about this when we talked about the psychrometrics a little bit. Sensing air versus sensing comfort. Okay, big difference. Humidity falls into play. Okay, heat load calculations involve only sensible heat. That's the heat you can feel. Sensible heat. It's the heat I can measure with a thermometer. Cooling load calculations involve both sensible and latent heat. Okay, cooling load calculations involve both sensible and latent heat. That's why we use two different numbers and two different columns for our heating and cooling load, as well as the different directions of walls, of windows and doors. Any questions on this slide? This is sort of important. Okay. Now, when we start talking about walls, okay, we have the red is my indoor, okay? The purple is my wall, and the blue is my outdoor environment. So when we have non-insulated walls, and I really hope you don't come across any of these, okay, my inside of my wall is also 0 degrees, and it's butted up against the inside of the house, which we're trying to maintain at 70 degrees. Doesn't work that well. Okay, if the walls of the buffer space are not insulated, we use the outside temperature. Okay, because it's going to be the same. No insulation. The walls are going to be outside temperature. The only separation is my sheetrock. Insulated walls. Okay, we have an insulated wall, and we talked about this yesterday. We use the average of the heated space and the outside temperature. Okay, we talked about this when we talked about crawl spaces and unheated garages. If I have an insulated wall right here, okay, my buffer space, which will like be a crawl space, attic, uninsulated garage, okay, would be halfway in between the 0 and the 70, because some of the heat is going to escape and some of the heat will escape to the outside as well. So there's going to be a constant movement, but the safe thing to do is use a temperature of the halfway in between. Okay, so buffer spaces, crawl spaces, unheated garages, and attics. So if I have an inside house, if my house temperature is at 70 degrees, I have an insulated crawl space, okay, and I have insulation around, and my outside temperature is 0 degrees. Could I install something that's going to freeze in this crawl space? Could I install anything with water or something that's going to freeze in this crawl space?
No.
Why are you saying no? It's not a wrong answer, but why are you saying no?
Because it's only 3 degrees above freezing. The outside temperature is 0. It's gonna. I have a room similar to that right there that butts up to my garage. That I know if I don't keep the heater on in there in these colder months, the pipes in the wall that butts up to the garage and the outside of the house, those pipes freeze, so I can't use my washer. So I would say no. I mean,
that is
contradicting myself a little bit, but
well, no, that is actually the correct answer. Okay, because this is just too close. I would not want to take a chance that this outside temperature is not going to drop to a -10.
right.
Okay, it's just too close. The reason I keep asking about installing things that are going to freeze, and you're going to hear me say this over and over and over, also in a little bit of the next term, you're going to hear me say this, is because when we install furnaces, if you install a high-efficiency gas furnace or a high-efficiency oil furnace, where we're talking about it's a condensing furnace, it puts off water as it burns, these furnaces will freeze in areas like this, and all of a sudden you get a no heat call on the coldest day of the year. Okay, it's a pretty bad situation. Okay, because the water inside the furnace will freeze. I wouldn't put a boiler out here either for that exact same reason. Of course, if I had a boiler out here, the heat, it would probably be warmer, but I just wouldn't chance it. Okay, so I never installed that type of furnace in an unconditioned space. Now, we see a lot of air handlers, that's the air conditioning side of things, installed in people's attics. I see a lot of now two-story newer construction where they've installed furnaces in people's attics, and sometimes they're very high-efficiency furnaces. Guarantee you, if you're working in this type of environment where attics freeze, you're going to want to carry a roll of pipe, the pipe warmers, that the electric pipe warmers that you can wrap around the pipes. You're going to want to always have a roll of that in your truck, because one of the things you're going to do every single winter is you're going to follow the installation team around, and you're going to end up wrapping the condensate pipes, because they will freeze and it will cause no heat situations. So again, that's why I talk about this buffer space, and I keep hammering this, because people forget about the fact that even though it's close, it's going to freeze if you get outside of your design temps. Okay, now, if you have a common wall adjacent to a buffer space with a significantly different set point, okay, it changes to delta T. Okay, so again, common walls, it's a little bit of a different situation. Okay, so if I have an insulated wall here, and I have an insulated wall here, okay, but no heat in here, no heat. And I'm just going to put H because it's tough to draw with the mouse, or tough to write with the mouse. But I have no heat in this area. Okay, but it's insulated. It's a common wall situation. It's going to be a little bit different. It's no longer an average because I have an insulated wall. I've seen a lot of garages built this way where they do insulate the outside wall just in case someone may want to heat it sooner or later. Good contractors will do that. Okay, it provides a little bit more protection. Could I install a furnace in this area? Could I put your washer in this area or whatever? Yeah. Okay, because there is an insulated wall here as well. So I would be comfortable in doing that because the temperature is high enough. Now, if some fool leaves the garage door open all the time, then all of a sudden this will become -10 and it might cause problems. But again, I cannot design based on the mindset that someone's going to leave that garage door open. The door's there, it should be closed. Now let's talk about zones. Okay, when we're talking about zones, we're talking about areas that are probably going to have a different temperature. Okay, for example, some people really like having a colder bedroom. Okay, at night. They like sleeping in a really cold bedroom. Some people hate sleeping in a really cold bedroom. Okay, so those are all different zones. Okay, a living room. A lot of people want it to be warm, comfortable, and inviting. While on the opposite side, I want to keep the bedroom a little colder. Okay, Laundry rooms, we don't necessarily need to heat up as high as the living room. Okay, basements might be different temperature controls. So that's what we're talking about, zones. Okay, now, forced air systems with ductwork are notoriously difficult to zone. We're going to talk about this more during the air conditioning side of things. For our heat load purposes, we are not worrying about zones, okay? We're not taking that into account. Everything is a single zone. In other words, we have one thermostat, one system, one source of heat or cooling. Okay, but in real life and in higher end construction, you may want to put in different zones. Upstairs has a different thermostat than downstairs. Okay, so just be aware, each zone should have its own thermostat. But the key is there must be a reason you zoned it. Okay? Don't zone just to add extra thermostats. It's going to cost more than it will save. There is a heat and cooling loss every time you zone a piece of equipment. Okay? The zoning can ensure that the thermal energy is supplied at a rate that matches the rate of thermal loss. Different parts of the buildings, especially in large commercial construction, can have different rates of heat loss. Some areas can become too warm. Some areas can become too cool. So again, there must be a reason you zoned it. Heating and cooling set points might be different. Time of use is different. Again, bedrooms, you're in them at night most often. Okay, time of use is different. Loads are significantly different. Could be due to solar gain. Could be due to internal loads. Could be due to use. All of these are reasons to zone buildings. But again, most often in residential construction, unless you are using ductless splits or supplemental ACs and heat, it is difficult to zone a system. Of course, if you have hot water, it's really easy. But then you lose the capability to air condition easily. So again, we need to take a look at zoning, because the newer construction, the newer buildings, the larger buildings, the commercial buildings, all are zoned. We want to make sure internal heat gain is taken into account. Okay, heat gain is generated by activities within the space itself. People are a large source of heat gain. If you ever walk into a movie theater, if you can afford to, okay, if you walk into a movie theater first before the movie starts, it's cold. Okay, we do a thing called pre-cooling of movie theaters. Motors, large electrical motors, have heat gain. Okay, they put off heat. Stoves, computers, lighting, all of this is sources of heat gain. Okay, does not include solar heat gain. Okay, because we deal with that separately. Solar gain, the increase of a temperature in a space or object resulting from solar radiation. That's solar gain. Thermal mass. Okay, thermal mass, two structures of identical size but different materials can react differently to temperature variation. A wood frame building will warm up much faster than a heavy block building and will require the addition of less energy in the process. However, the block building, the stone block building, will remain warmer after the furnace shuts off. The same effects are true during the cooling season. If I have a wood frame house, it's much faster to cool because of the thermal mass. Okay, because I have to cool the walls. But it's going to remain cooler different lengths of time. Okay, that's why I care about the thermal mass of a building. Okay, you keep hearing people say heat rises. Well, actually hot air rises. It's lighter. Okay, it's called stratification. We've talked about this. hot air rises, it finds cracks. So again, when you look at your houses, okay, I know I saw a couple pictures of some areas that probably in some people's houses, when you did that identification of things that could cause air quality problems, a couple people had whole house ceiling fans. Got to seal them when they're not being used. And I know the pictures I saw, they were sealed. But just want to point it out, got to seal them when they're not being used. Because it's going to find cracks in any place to exfiltrate. That means leave the building. The cold air replaces the hot air. Okay, so all of a sudden I'm going to be sucking in through cracks and crevices or through the floors from the basement, and everyone's feet is going to feel cold because the hot air is all exiting the top of the house. That's stratification. It's also called stack effect. Air exchanges are important. Okay, so far we've talked about transmission losses. Losses through the planes, that's the walls, any part of the house. We combine the loss, okay, for a total building loss. This is what we've talked about so far. Now, we got to talk about air exchange. Transfer air is either intentional or unintentional air movement from one space to another. Okay, it's not outside yet. Transfer air is just movement of air through ductwork or just through stack effect from one space to another. Okay? Ventilation is intentional. Okay, we want to ventilate. We use two ways to ventilate, natural or mechanical. Natural means we have a dryer vent looking thing down at the bottom of the house, and we have an exhaust up at the top of the house. Doesn't have to be motorized. The cool air will come in at the bottom and leave through the top. Natural ventilation. Other time of the year, cold outside, cold air comes in, drops, and leaves at the bottom. Again, we can cause, both times of year, I can cause air patterns in a house if I do this properly. Natural ventilation. They use very, very heavily in European countries. Okay, they know how to do it. Okay, here, our contractors much prefer mechanical ventilation. Okay, it's easier. You don't have to size it as well, and you don't have to understand buildings. They stick in a ventilator fan. But ventilation, okay, exfiltration and infiltration is not mechanical. It's not controlled. Okay, it's air that's leaving my house, my controlled environment, and going to do something else. Okay, so this is non-controlled air. Okay, air leakage is the rate of infiltration around a window, door, or skylight. Air leakage, it's the rate of infiltration. The total, so air exchanges per hour, and I've used this before, it's the total volume of air in a building that's turned over in one hour. Okay, ACH, total volume of air in a building that is turned over in 1 hour. Very important. Okay, new formula. Okay, infiltration or air exchange rate, depending on how you look at this, is the volume of airflow moving divided by the volume of space. How do I find the interior volume of a space? You take your square footage based off of your building plans and multiply it by wall height. Okay, so you already have your square footage. We've done those measurements. Okay, to find the volume, interior volume, you just multiply it by the ceiling heights. Some of you have cathedral ceilings, you have to figure out what the area is, okay, and what the volume is of the triangle. Okay, you can sometimes guesstimate it. These are not perfect numbers. Load sizing is an estimate. You want to be close, but again, there is room for error. Okay. ASHRAE publishes a guide. You can find it online. Okay, I'll give you some numbers as we go through the rest of this course, and I may actually throw a chart up there, but there's ventilation standards that are specifically designed for residential, commercial, different uses, different parts of a building. This has all been thought out by the engineers. You don't need to recalculate this stuff. This has all been thought out. Okay? Building volume is calculated by multiplying floor area by floor-to-floor height, floor-to-ceiling. Okay? It's a conservative estimate. And again, here's this word. This is why I keep telling you guys it doesn't have to be perfect. It's a conservative estimate of the enclosed air volume, because wall and floor volumes are included in the total. Okay? More precise calculations you can do, but are normally not justified. It doesn't make that much of a difference if you're off by a couple feet. Okay? So volume. Okay, airflow is where we're going to leave off today. Okay, you're going to be estimating the rate of airflow. Okay, but it depends on the quality of construction, the age of the structure, and the direction and strength of the wind. There's a lot of variables with airflow. Okay, typical airflow ranges from 0.5 for new construction to 1.0 for older leaky buildings. Okay, and that's not a slam on the buildings, that's just reality. Okay, so we're going to be using these measurements as we go forward. Okay, and I think that is where we are going to leave off the slides for today. I've probably talked about